Thank you very much for making me talk, and thank you very much for being here. So, most of the work will be collaboration with those three authors, Habib Amari, Eric Bontier, and Marcus Vogelus, and not three all the time, but and sometimes others, so I will mention them too. What I call review is because I have almost zero claim to any work on those parts. It's just that it's just to show you what other people have done. So I will start with explaining what the problem is in general, and or part of the problem is what do I mean by imaging? On one example, which is the simplest one, which is electric impedance tomography, and then we'll move on to a simpler problem, which is when you want to find small things, and then that will be the first part, and the second part will be a link between this and another question, which is called time reversal. So one good thing in inverse problems that we are good with fancy names. So we do cloaking, we do invisibility, we do time reversal, we do things like this. So it's so I'll explain what the words mean, and then I'll explain a little bit how you can combine all the 3 points above to have good resolution effects. Okay, so what is impedance tomography? Well, let's start. Simplest example would be elastic tomography. If you want, you knock on the outside of the pulpit and you wonder where the computer is. That's what you do. And so what you do is you put an impulse and it vibrates, and what you hear is a vibration. So, but you could put sensors and tapping here and there, you could feel it is empty or plane, and that's the idea. So in electricity it's the same, only you do it with current. And so you have a bounded domain. You don't want to cut it up, so you want to stay outside. You have a non-conductivity inside, and you impose a current, and you measure the potential difference on the outside. Or you impose the potential, you measure a current, whatever is more convenient to do. Okay? So this is a conductivity equation. Gamma is your conductivity or your impedance, 1 over the impedance. Phi is your current, which is on the boundary. And what you want to measure is U on the boundary. So if gamma is a positive bounded function or matrix, and if you say that the sum of currents equals 0, so that your problem has a solution, because you have a kernel, then you have a solution U, which is well defined up to constant, and it's in H1, so it has a trace on the boundary in H1 half. Very good. So now you vary phi, and you obtain different U's, and that's a map. That's a map from the boundary to the boundary. And this linear map would be, so this is a Neumann boundary condition, and this would be a Dirichlet boundary condition. And so it's a Neumann to Dirichlet map.
So, sorry, we're trying to determine gamma? Or
gamma, yes. This is given, right? You can knock as you wish, and you can hear what you can. Right. Question is, what is gamma? Mm-hmm. Right? And so first question is, can you? Right? Can you find gamma? And
so let me just make sure I understand.
So you have all sorts of, you have the map, you know the range of the map. You know a full map from H1 minus 1/2 to H1 half on the boundary. Mm-hmm. And of course it depends on gamma, right? Because U is a solution of the equation inside. Yes. You just measure it on.
You're saying if you know the map, then you find gamma, right?
Yes. Can you? Yes. Mm-hmm. Okay. So let's start by saying no. Yes? No? What is the problem?
But you do know something about gamma?
No?
Because previously said provided gamma is positive.
Yes, well, it's conductivity, so you don't have negative conductivities. You know, it's but you just said generally, you don't assume any irregularity, you just say it satisfies the conductivity equation, which means that gamma is a bounded matrix. That's it. Yeah. Okay. So let's say you try to do it in 1D. And in 1D, the answer is no, because in 1D, this is an ODE. You have two independent solutions, so you can make two measurements. With two measurements, you will never find a function and an interval. I mean, you find a constant of that function. Actually, you find the average of it, and that's it. So, no. In 2D, or in more, well, try to see what can you do. You could imagine, okay, can I find gamma, or can I find gamma up to a change of variable? And so imagine you have a change of variable from omega to omega, which keeps the boundary the same. So the f of x is equal to x on the boundary, and does something else and twists it inside. Well, if you look at the rational formulation of this, it is unchanged by looking either at gamma or at the transformation of gamma through the change of variable. It is the same. This is just the formula of change of variable, right? So up to a change of variable which would keep the boundary intact, the answer is no. So you can only find something, well, okay, so what is a good problem? The good problem is if gamma is a scalar, because those are matrices. And so if you restrict yourself, either you say matrices and then you restrict all the possible change of variable, or you say, I take gamma a scalar, then can I have a positive answer, right? Scalar function. Now, this is the inverse problem, which is to find gamma. We haven't said yes or no yet. But it already tells you what to do if you don't want to find gamma, if you want gamma not to be found. It tells you that the smart thing to do to hide something is to design a completely anisotropic material which would have an equivalent scalar equivalent, which would be the same as nothing, right? So if you can design a coating, a paint or something, which would be very anisotropic and would basically make this change of variable so that you would basically see nothing of what is inside the subregion, you'd be done. Okay? And so that's possible. Well, that's possible in principle. I mean, you can design such a change of variable, which would, what is the idea? The idea is basically you take you make a change of variable which would change a small disk of radius little rho to a disk of radius 1, and outside of a radius of disk of radius 2 would be unchanged. And then you apply the inverse transform of that. And so anything which would be inside the disk of radius 1 is pushed back to a small disk of radius rho, scalarly speaking, right? And then you make rho to go to 0. And then it's a point, and you've lost it. Okay? Well, okay, so in fact, you can't really make rho go to 0, so there is a small trace, but basically you can hide very much whatever you want.
I didn't quite understand it. So how does this work again?
Okay, so if you have, say, now the question would be, what would be cloaking? Cloaking would be, how do I design a material which would, from a measurement perspective, look like an empty material? So you design an anisotropic material, which would be a change of variable which would look like this, which turns things around. You put whatever you want inside the subdomain, but your change of variable maps the subdomain. I mean, maps a big domain to a subdomain of very small size. Basically, it's an homotopy if you want, which shrinks a domain of size 1 to a domain of size epsilon. Okay, and if this material looks from a measurement perspective as a scalar answer, because that's all you can hope to get, like something with a very small point where something is not right, but then you make this point go to 0. So in principle, you could. Okay.
But is this how stealth works too?
Yeah. Yeah. Exactly. Well, you can't do that. Well, the question is at which frequency can you hide things? But this is 0 frequency. You could imagine to do that. But I mean, we can discuss how well does it work, but okay. So this is your what the problem is now, which is if you have a scalar gamma, can you find it? Okay, and the surprising result. So this question was asked in the 50s or early 60s, and in 2006 in Annals, Kari Astala and Asipai Varinta showed that yes, in general, meaning that if you have gamma in L infinity, in 2D, indeed, you can, in principle, recover gamma from boundary measurement.
Gamma has to be scalar, right?
Gamma has to be scalar, of course, yes. And yes, that's it. but that proof answers nothing about the 3D case, because it is completely linked with the fact that you're in 2 dimensions, and therefore you have complex analysis, and you have quasi-conformal mappings.
And does the proof also give you a way of finding out what gamma is?
Yes, if
is it sort of well posed?
Okay, very good. So this is coming in this quick. So it tells you. So of course there is a method to construct, but what does it tell you? So before I answer to what it tells you, what is the situation in dimension 3? It depends on gamma, meaning that if it's piecewise analytic or if it's relatively smooth, Lipschitz, for example, then the answer is yes, and you don't know in general. You don't know.
What if you had like a cube or something? I mean, something like the edges and so forth. That would not be good for this method.
Which one? The 2D one or?
Yeah, 3.
The 3D one. If it's piecewise analytic with corners, well, in each single case, I guess you can cook up a method to find it. If you tell me I have such corners here, then yes, but it's very difficult to, but you cannot, if you say I have X corners and I know it's a polygon, then yes, actually, you can do it easily because corners are easy to pick. Okay. And so if you find, they are very singular. And so if you know you're looking for corners, you'll find corners. But if you don't know you're looking for corners.
so you have to have different algorithms or what?
Yes. I mean, there is no algorithm telling you what to do in 3D. I mean, there is a general method which works for relatively smooth coefficients.
Well, I mean, often you would look for edges or something like that, right?
So if you look for that, no, there is no general method for edges. Well, you can, if you know you're looking for certain edges, yes, you can find things. You can derive different algorithms, but it's not the same thing as. It's completely different from trying to answer the question in general. Actually, if you limit yourself to polygons, it is well posed, but but it's not the same as saying I don't know what's in it, right? Okay. But yes, so is it well posed? So what is the definition of well posedness? Does a solution exist? The answer is yes. You know gamma exists. That's how your data was created. Is the solution unique? Well, maybe, probably. Let's say it is. At least in 2D it is. And thirdly, does the solution depend continuously on the data? And that's very hard. That's very hard. And Adama looked at the Cauchy problem. If you have a boundary, if you look at the heat equation and you say, I have Cauchy data, does my solution depend continuously on my Cauchy data? And he cooked up, it's easy to create an example where actually your solution would go to 0 or go to plus infinity where your data stays bounded. So it's not stable at all. And in the same manner, in this example, which was exponential, you can prove that even if those 3 points are true, you cannot expect more than logarithm dependence, meaning that at best, if a general algorithm is found, you can already say that if you try to find, as the perturbation argument, the difference between gamma 0 and another gamma that you would cook up, you would be the difference, the stability with respect to lambda is as much logarithmic. And for numerical analysts, the logarithm doesn't converge to doesn't go to infinity. It's a bounded function, because with any measurement data, a logarithm is a bounded function, right? 10 to the minus 16 is just minus 16.
So this is for even for 2 dimensions, right?
Yeah, in any dimension, yes. No, it doesn't answer. So the fact that the theorem is true doesn't answer the question at all.
I understand.
Unfortunately, yes. So you cannot. So because of this, it is severely ill-posed in general. So you could decide, well, I'm going to change the problem in one or another, regularize it, or add extra data. And regularization is very popular. It fits most optimization problems, but you but you lose the connection with the physics, if you want, because since you add an extra term which isn't there, except if you design your regularization to be exactly matching the problem you're looking at, it's actually very hard to do one which is very efficient.
Now, I had an L2 type of theory. Is that easier? Is that better?
Not. you want, I mean, if you want to find
I
your,
don't know what, I mean.
you want to penalize something in L2?
Can you have cruder distances rather than L infinity, for which this converges better, I guess my question.
You have a lot of local minimizers everywhere. And so it's mirrored with, the problem is that the solution of the initial equation is analytic with respect to gamma in L infinity, meaning that the perturbation of U, in fact, it's linked to the fact that you can make measurements if you want. If you have a good measurement, it means that if you measure the same thing twice, it will give you the same answer. Which means that if you have changed a little bit the conditions of the world around it, it hasn't affected your solution. That's very good to make good measurements, and it means that the inverse problem is hard, because it means that actually small changes do not work. So good measurements mean difficult inverse problem. I mean, that's ooh. Okay. Well, so that's a terrible picture, which I'm sorry about. So let me draw the picture on this. So let's now move on to say, let's look at a simpler problem. I had a very nice picture, but this is more, this is an homogenized one, yes. So let's say you have a domain, and you have all sorts of things in it. Okay. And but you make an assumption. You make an assumption and you say, well, I know what my conductivity is inside my domain. It's gamma 0 of x, almost everywhere. And then it's gamma 1 somewhere else in those subsets.
Would you assume there's high contrast or not necessarily?
No, you just have gamma 0 different from gamma 1, hopefully. But you have something else happening in a subset, okay? Omega epsilon. You don't look at things next to the boundary, because in the boundary, this is an interior result if you want. So next to the boundary, actually, if it's on the boundary, you can find it. So, but you say you stay inside the domain. You want to take internal measurements, and the assumption you're making is the place where you don't know what things are is small. So the obvious application is finding tumors, for example. Is that you globally know that you have healthy tissues, and you want to find small, hopefully a small place where tissues are different and have a different behavior. Or you want to find a mine, or, you know. The applications are different from different periods. I guess in the 80s, people wanted to find tanks in deserts, and now you want to find tissues, healthy tissues in biology. So first step is the agreed idea is that what you want to do is to understand the direct problem. How does the solution behave with when you change the conductivity in a small place? How does that affect your solution U epsilon? And to characterize the effect of changes on a small volume. And from this characterization, hopefully you will be able to design an ad hoc method to find what you want to find. Okay? All right. So what do? We say, we know the solution if I have gamma 0 everywhere. So this I can measure. This is data from a healthy body, if you want. And this one is the one with defects. Okay? And so what we do is we make a difference measurement. We measure the difference between the good case and the case with defects on the boundary data. Okay? So there is no, it is not singular. So you can prove easily that if the difference of conductivities go to 0 in L1, I mean on a small, yes, in any LP but L infinity, well, your gamma will go to gamma 0 in all those LPs, and your U will go to U0 in H1. So it's not a first order term. So it's not a zero order term. So there will be a trace which will depend obviously on your volume. Okay? And so what is the result? The result is that you can in fact show a formula which explains, so I will explain how you derive such a thing, but which explains what is the signature of those defects. So it is in terms of the volume, omega epsilon, It depends on your contrast, gamma 0 minus gamma 1. Okay. What is n? N is a function you use to localize things on the boundary. So it's a green function, if you want, on the boundary. So it's a Neumann function, which says that this is how you localize your u minus u0. Okay. So by definition, u0 is u0 of y is sorry. u0 applied to n applied to g gives you u0, right? So this is your Neumann function. What is mu? So you have something which with a measure mu. Mu is the limit of the support of your inclusion. So it's a compactness result, meaning that, of course, if you have two inclusions, if you look at a sequence of domains where the inclusion is oscillating between right and left, you have to have a subsequence for this result. So it's a result of compactness. So up to a subsequence, there exists a subsequence such that you have this limit. Okay, but if you rescale the indicator function of your inhomogeneities by its size, well, this has obviously total mass 1, and so it gives you a probability measure mu. Okay, it's easy to see that it has a limit in L1, and so well, so it's because it's L1, it's just in the sense of measures.
No, I don't know. I haven't figured out what all these things mean. So what is the M? What is the M?
Yes, that's.
Where is it?
What is M?
Yeah.
Yes, it's coming.
Oh.
So u0 is u0.
Okay.
I'm happy that. So u0 is u0. N is a green function. Mu, we're happy. Gamma is a contrast. And so the only thing that you haven't discovered yet is M. And so what you can say is that M is a function which is a matrix, which is L2 of d mu. You can describe different things of it. And M, of course, is the thing which describes your inhomogeneity, right? This is what describes the location of it. And this is the matrix M describes, well, it contains the information. The geometric information or the contrast information inside your inclusion is defined in M. Okay, so information on M will find you information on what you want to find.
Oh, but I thought that was all contained in the gamma.
Gamma is gamma, but gamma is just is a value, right? So imagine
So gamma is
it could be 3. Imagine gamma 1 equals 3 and gamma 0 equals 1.
Yeah.
But it doesn't tell you if you are looking at an inclusion which is a star shape or which is a grid or it's distributed everywhere, right? So that depends on M.
How do I get this Mij? I mean, it depends upon the shape of gamma or not?
Yes.
Yes.
So very good. So how do you get Mij? So what does the formula say? It tells you that you have separated two things. You have separated your u0, your inclusion, from your background. So you have, if you come from homogenization, you would say you have a separation of scales because you have separated u0, which is the general behavior without the inclusion, from the effect of your inclusion, which is M. Okay. So separation of scale. Why? Because u epsilon goes to u even in rescaled by the volume in L2. That's strong. Okay. So you have a strong convergence of u0 to u. However, you have an effect on the gradient, and so your gradient is polarized. Gradient u epsilon is polarized, and the difference between u epsilon and u0 shows in M, if you want. Of course, the contrast is in it, and you have M, which will twist your field, your current, if you want, in a certain way. Okay, so what is M? What is M? M is defined as okay, so before I come back to M, one thing is that it really depends only on the inclusion. It doesn't depend on omega. M is independent of omega, the big domain. If you take a bigger domain or a smaller domain, which is around, which still contains the inclusion, it's the same M, right, up to volume. It doesn't depend, of course, on the boundary condition. It's really a geometric information. So it depends on gamma 1 and gamma 0, yes. But it doesn't depend on, point-wise, right?
So right now you're talking about the direct problem, but
yes.
when you think of the inverse problem, you
Gamma 0 is known.
And gamma 1 is. So what-
Gamma 1 can be not known or, well, okay, so yes, coming back to the inverse problem, you see that you have gamma 1 minus gamma 0 times m, okay, times the volume. So first thing it tells you that a bigger inclusion with a smaller contrast or a smaller inclusion with a bigger contrast has the same effect, right? If you multiply, you have at first order, the difference of contrast and volume is the same. So they have so you have to, if you want to find the volume, you have to make an assumption on the contrast or vice versa, right? But if you want to find the orientation of things,
But you're assuming something about gamma 1
no,
as
it's
a dependence of gamma 0?
gamma 1 is just a function. But I mean, here you, okay, so to write this formula, sorry, you need gamma 0 to be relatively nice, meaning that actually you want gamma 0 not to be general infinity, but somewhat smooth. Well, it's, yes, somewhat smooth. So for example, C0 is enough, but you don't need as much as C0, but C0 is nice, okay? You need your background to be a nice background, because if your background is very contrasted, then putting an inclusion on it will change dramatically the behavior of everything. If it might smoothen out some singularities, therefore change completely the order of things. So you want your background to be reasonable, and then you can find what is the effect of perturbations. Okay? So what is M? M is defined as a, so if you know homogenization, this is the same definition as the corrector functions in the periodic setting, if you want. It says, so let's introduce a function v, which has the same divergence as gamma 0 gradient x. So if you want, you're looking at the effect of you're rectifying the gradient, you're rectifying x gamma 0 along gamma epsilon. Gamma epsilon is the one which has gamma 0 and gamma 1 inside the inclusions. Okay? You take this function, you show that you have the correct estimates and that they exist, and that defines M. Okay? So this definition is independent of the boundary, and you can make it independent of omega because it's you can just decide it to be on a square or anything. Okay. And this is your how you define M. And now, why does this problem play?
You don't know what M is either. I mean, because you don't know what the gammas are, right?
Well, actually, you know a lot of things about M, but you can show a certain number of things about M. But okay. You don't know M in general, but you can find, I mean, yes. Let's see what you can find about M in a second. So now that you know what M is, well, okay, so.
But I don't see how you can find an M if you don't know what the gamma is. You're looking for the gamma, I thought.
You can find, well, okay, so you can decide one thing or the other. You can say, if I know gamma 1 in my inclusion, can I find the shape of my inclusion? Or if I know or if I don't know the shape, can I give a bulk estimate of what is the contrast times omega?
Yeah,
So that means that you have to prove general properties on M independently of gamma, which you can. So if you make general estimates on M independently of geometry, for example, then you can prove, then you can obtain properties in general, right? So it's not empty.
It's independent of. Well, let's say you have a magnitude of gamma, but then you have the shape of it, right? With new.
Yes, but if you can make something which is shape independent, if you can show what M is or bound M in the function of gamma independently of shape, which you can, then you can get informations in general, right? But already what this formula tells you is that really it's located on the inclusions, and that the general field that you want to look at is U0. And so whatever you get as information on M will help you locate things. But for the support, in fact, you have already reduced your problem a lot because, well, imagine now that the limit mu is a sum of Diracs, right? That I have a few inclusions. This could be, in this general setting, mu could be anything. Could be the global Lebesgue measure of the set, right? I mean, and then you would have a dilute limit or an homogenized medium. But imagine that it's a few objects, and so say that in the limit, mu is concentrated in, say, 10 points. Well, you have a Dirichlet to Neumann map, which now you have represented as a finite range operator with a range 10, I mean, at first order in terms of volume. So you have switched from, so you have a surabundant data to find the finite range operator, which is located on the inclusions.
Finite range, because what you're going to replace that interval by some sum, right?
Because if that's a Dirac mass, it's a sum of Dirac mass, it becomes a sum, yes. A sum which is a number of my inclusions. And so if you have a finite range at first order, of course in the volume, then you're happy. I mean, you can hope that changing your data with, say, twice the range, you will find exactly everything you want. You know, you don't need that many measurements to find 10 objects, basically.
Sorry, but confusing notation. When does the function which you denoted phi previously enters
into u, right? U depends on phi, right? U0 is a function of phi, or g. Sorry, g is phi. G equals phi. My current is g or phi, right?
So that's phi.
Yes.
So could you show the equation?
So so now this is my Dirichlet data, u on the boundary. What is my Dirichlet data on the boundary? The function of g or phi. It depends on something inside, obviously. It depends on the difference of conductivities located on the support of the inhomogeneities, where my field u0 is twisted by my matrix M.
Enters only is there anything in this formula except for u0 and u epsilon which depends on
No, just u0.
Oh, U epsilon also doesn't depend on.
U epsilon, of course, depends on, it's measured with the same thing, right? We make the same measurement. We make the same measurement, one with defect, the other one without defect. Or, without defect, with defect. Yeah?
Okay, we just have to be reminded about those. Okay, yes.
Yeah? Okay. All right. So, how do you prove the representation formula if you want? So, let's ask.
Before you prove it,
Yes?
once you have it, what I don't quite see what it does for you.
So, it does two things. Yeah, okay, so it does three things. The first thing it does is that it tells you what is the range of your operator. The range of your Dirichlet to Neumann map is, say you have, say, n inclusions.
Right, it has,
So it is, the range is generated by a Dirac mass located at the location of my inclusions, and the shape of it is vectors, which are the gradient of u0 twisted by m, okay, times the contrast and the volume. And so if you know this information, you can decide to find it back. You can decide to find those inclusions by testing, using phi, smart phi's as boundary functions to locate it.
So suppose we just have some fixed number like
Yes. Yes.
five defects, right?
Yes.
5 local defects. So then how do I so now I want to find out where they're located, right?
Yes. Yes.
And
Okay, so
so you can count the number by looking at the rank of this thing, roughly.
yes, and you can also find them because, in fact,
yes.
this is those. If you this is okay. So if you look at the operator, okay. So if you look at your Dirichlet to Neumann map, the eigenvalues of this operator, the eigenvectors of this operator are exactly the Dirac masses located in your inclusions. The first n eigenvectors are Dirac masses located in the inclusions. Thus, if you make a spectral decomposition of an SVD of your operator, you'll find your inclusions. I mean your location. And if you want to find the contrast of the shape, then you have to try to see what is, now that I know where they are, can I do something else and find where? Okay? Okay, so what is the proof? I mean, without any technical details. So V epsilon and V0 have the same divergence. So I can test them against any function, for example, U epsilon and U0. Look at the definition. I test it against U epsilon minus U0. They have the same boundary data. divergence of gamma epsilon v epsilon equals divergence gamma 0 v 0.
Because they're
Hi.
all zero.
No, this is the definition of v epsilon, right? V epsilon is this function. This is x.
Oh, okay.
V 0 is
Yes,
x.
yes, yes. So,
I test it against this function. I test it against anything. I get, of course, the same integral. Why not? Now, u epsilon is gamma epsilon harmonic, if you want, right? So this one will give me a boundary condition, which is the same as u0. So it should simplify into gamma epsilon minus gamma 0, u0, gradient v, right? Just integration by parts. That's just using the equation, the connectivity equation on u epsilon and u0. Okay, same calculation here. Only here I have gamma 0, so it goes well with u0, and it leaves me the u epsilon. Right? Gamma 0, u0 is most gradient, gamma 0, u0, v0 is mostly 0, except the boundary condition, which is constant by u epsilon. And so since it's 0, 0 is also a gamma 0 u epsilon. Yep. Very good. So now what do I have? On the right-hand side, this is gamma 0 minus gamma 1, indicate a function of my set, v epsilon. So that's the definition of m, gradient u0. What do I have on the right-hand side? On the right-hand side, this is x. This is gamma 0 minus gamma 1. The only thing which depends on epsilon is my u epsilon. So this is exactly what I wanted. Okay. So of course, this is the same thing as the compensated compactness method, meaning that you put everything on the test function. You choose a test function which mimics your behavior, and that solves the problem for you. What is missing is why those conversions work, and the fact that actually it's not an average thing, it's true pointwise. And so you have to do truncations and all sorts of things, but that's why it should be true. Okay? All right, so what is my m? We know a lot of things about m. So this picture is m in terms of its eigenvalues. So it's a 2 by 2 positive decimal matrix, and I say fix, so what are my axes? This point here is gamma 0 over gamma 1, and this point here is 1. So in this case, I have a contrast which is greater than 0. And this line here is an inequality on the trace, and this line, this curve here is an inequality on the inverse trace, which are simple to write. I mean, it's another talk to explain all this, but
I'm not sure I understand what this picture means.
okay. So this is a set of all possible m's. Given
Instead of all possible.
this is the G closure, if you want, the set of all possible m's that you can have given a contrast. Right? They all lie in terms of eigenvalues between those two values, between in this half moon or quarter of a moon, right? So it gives you. So there is information independently of geometry. This is if you have a geometrical information, you can do more. You also know a different thing, meaning that if it's isotropic by symmetry, then of course you're in the middle. The less isotropic you are, the more you go to corners, right? So the very anisotropic things are long rods, right? And so if you have a long flat rod along one direction, you'll be here, and you can calculate its eigenvalue, which is 1 and gamma 0 over gamma 1. This is a symmetric one, right? And you can show all sorts of things. You can show that actually, if you go towards this end of towards this side of the bounds, then this is thin objects, meaning that you cannot have. It has to be something looking like either a mesh or a rod or a set of rods. It cannot have any ball inside the object that scaled ball, of course, right? It cannot be a large.
Depends on the points of function. So we would do if it were.
So say you're looking at a simply connected object, which would give you m.
But m is a function, right? So
Yes, but
at one point it can be.
okay. So it's a function, and now I want to say it is true. But now let's say I'm looking at one object, and I want to say what is one object with this m in x, right? So m is I'm at one point, and it corresponds to one shape which shrinks to a Dirac. Then m is a constant matrix. And what does m look like for different shapes? Okay.
Oh, you fix the location of.
Say I have a fixed location, and I shrink an object, for example, right? I shrink its size to 0. What happens? So what I'm telling you is that if you are what does the tensor look like? So this is the eccentricity of the tensor. So if it's more isotropic, if your object has more symmetries, obviously the two eigenvalues will be equal, and so it will be on the central line, right? And if it's less isotropic, you'll go towards one of the edges, and to be less isotropic, you have to be at the end. You have to be flat, right? And to look like to be very thin, if you want. And this one is easy to calculate. Those two
That's along that line, though, right? That's along the
it's the intersection of the line and those two curves, right? So what do you have here, right? The more if you get very thin, you have no choices. You have to move to. You have to have a big difference between your eigenvalues, and you're moving towards the end. So thinness makes you go one way. Now, I mean skewness, right? Now thinness makes you go up, meaning that if you are here, you have to be thin. You cannot be not thin and be on the upper part. And there was a now the question is, what happens here? Is it the thick objects, like balls and ellipsoids? So in fact, you can show that you can calculate that yes, ellipsoids are exactly here, and this is a disk. And there was a conjecture which was by Pauli and Zeger saying the minimal object. So this point, if you want, is the minimal point. The minimal object has to be a disk. If you are at this point, if your tensor is this point, then you have to be a disk. And well, so it's a long story, but the answer is yes, but it's a very bad answer because it's true, but it's only true. No, we can discuss it afterwards. But it's true, but you can perturb it to about nothing and get an object which is nothing, looks nothing like a disk, and which is infinitely close to this point.
really opposed.
Yes, yeah. So it's not a stable conjecture, if you want. Okay, so okay, and then so this is first order. Now, if you have one type of object, you can try to do higher order estimates and get more information, separate contrast and size and all that. But in general, that's as far as you can go. Okay, so now I consider that we know everything there is to know about impedance tomography, and you have understood completely small inhomogeneities. And so let's talk about something else or similar ideas, which is time reversal. And so this is it comes from physics. It comes from an experiment in a water tank by Claire Pradin and Matthias Fink. And
Put the lights on over there.
yeah. Yes. So they have a water tank. They put metal rods in it, which is random scatterers. They put a microphone, which sends a beep. So let me not just draw a water tank, but do it in 2D. So this is an anechoic chamber, meaning that your signal can bounce on the walls. This is your scatterers. This is where your microphone is. You listen to it on one side. Okay, these are recording microphones. Okay, so you emit a pulse here, and you listen to it for a certain long time t on that boundary. You amplify the signal, you simplify it, you play it back, and for a long time you see nothing, and at time 2t, POC! You get a localized, concentrated, focused peak exactly here, at the point where you sent it before. Yes.
Kind of amazing.
Okay, so very good. So of course it created a lot of activity because it's fun, and so
This is experimental.
yes. So you return your microphone into a receiver and you listen everywhere and so on. So this is Guillaume Ball, who is in Colombia, has done as on his webpage, if you want, there is a movie showing you. So you send a signal in a random medium. This is the front wave going out. You record things on the corner of your boundary. You play it back. You get scattered noise all the time. 2t, puff. You get a nice localized things. Okay, so there is books. I mean, Georges Papanicolaou is a big name of the subjects. And so there is a book by Jean-Pierre Fouque, Jocelyn Garnier, Papanicolaou, and Prince there are different articles. So Guillaume Ball, whom I quoted here, as a paper with Linear Rizik. In fact, the first mathematician to work on it was Claude Bardos with Matthias Fink, who explained that it's just the fact that the wave equation is reversible, and so he has worked on this with himself, and so he actually has a website with his name, and so the title is in French, Retournement temporel, but if you want to download the slides, they're in English and very clear about what happens.
So, but does it have something to do with the fact that all those were rods in there, right?
Yes.
Okay. Does it have to do with the fact that those are randomly placed or not?
Exactly. So as you can see, random is everywhere in those things. And so the big argument was that time reversal works because of randomness, and randomness helps you. So what would be
Time reversal works whether you have randomness or not, right?
Well,
That's what I'm
if you have an homogeneous medium without scatterers, no, it doesn't work. I mean, it would work, except that you would lose everything, because you're not measuring everything everywhere, right? You just have an array of microphones here,
Yes.
and so you would lose a lot. But in fact, because of your scatterers,
So it homogenizes the.
it gets a signal and sends and gets you more information. It's easier to find back things because of the reflections. If you want, the more complex medium says that basically you are not filtering to the first harmonics, but your spectral decomposition, if you want, is much more complex than in a nice homogeneous medium, and so every single lower the frequency.
You get more information, in other words, through
Yes.
because of this, and because you're only feeling it at some part. But
Yes,
but
for a long time.
yeah,
But-
for a long time.
But the projection on time of those eigenvectors, if you want, is much more complete than if you had a nice periodic pattern and a crystalline geography, where you would say, well, no, I can only get what Shannon Nyquist would tell me, basically, right? I could only get certain number of things independently.
Yes, if I took those scatters out and I made them periodic, then could I do the same thing?
I think so. And but this is not what is this is not the paradigm. And so
I'm sorry.
yes.
I tried to listen, but I kind of lost. So if you take out the randomness, so this effect will.
So if you take out the randomness and you listen to an echo, well, if I hide myself in an empty room and you're sitting there and you hear, "Ow, do you know if I'm here or there?" It's very hard. You know it comes from here globally,
Yeah.
but if I say two words or if you move a little bit, you'll be able to find me better. But because you have two ears, right?
Yeah.
But otherwise, you'll have just a vague idea, right? However, if there are many chairs around, and if you have a corridor and things, well, it's easier for you to know that I'm coming from this corner of the room. That's basically what he's telling you.
Excuse me, isn't the point actually the fact that you want to generate the signal returning to that point just placing just adding a source of a wave in those points? So I think the point here is that if you could put your sources, your detectors all around the box, it would be
The same. If you had a full,
without the inhomogeneity, would be good because there is this, I guess, Kirchhoff principle that you can start
yes,
a wave in each point and the sum is going to be the same. Now, if this is no longer true if you stay only on one side.
if you stay on one side and
you know the wave where it's coming from, but you cannot reconstruct just producing a wave in that point on the bottom.
no, you can't find its location exactly. No.
But you can because it's just if you have two detectors, it's enough. Because you know that the source was one point, one delta function.
No.
Point.
No, because
you know it was a spherical wave starting a certain point.
in an homogeneous medium, I agree. If you say you're saying you draw, you look at your wave coming from, but you could have, this is true if you have one scattering. So you say if you have an homogeneous,
Without scatter.
yes, so if you're in a homogeneous medium and you have 2 points, yes, you could do an intersection, but actually it's very, you cannot find,
No, but you cannot generate the think
well,
it returns there because you should start everywhere around the boundary.
yes, you have to, you can locate it by, yes, by triangulation, I guess, but, well, but you lose the location of it.
Something actually much stronger. You're saying that the way it refocuses.
Yes, it refocuses that point. Yes,
You work
yes.
with just 2 points, but you need all the boundary, or just one side, but
Of course.
Yeah, so
So-
that's really the stronger statement, I think.
Yes. Okay. And so, what is this pulse? What is this pulse here? This pulse is that. What does it look like? It's not a Dirac mass. It has a size, and you can show that the side of your focal spot, this distance here, is related to the display of the distance between your microphones and the frequency at which you look at things, which is lambda, and so the focal spot is lambda over 2. Okay, and this you can, by an integration, if you look at the green function, you can show that lambda over 2 is as much as you can hope for, and in fact you can get lambda over 2 in physics. I mean, in experiments. This is 2 teams of people, Henty and Stansil, and the Fink team also, published in the Physical Review Letter, the fact that you get lambda over 2, which is fantastic, meaning that you get the resolution you would hope for physically. Okay. So what does resolution mean? It means how far apart should be 2 sources to be identified as different in a time reversal experiment, meaning that if you have your array of scatterers here, and you refocus your wave, it will have a certain size. Okay. Now, if your wave has a size lambda over 2, if your 2 points are close, are less than lambda over 2 in size, it will be hard to know if it was from this point or that point. Actually, up to noise. And so, resolution means the size of your refocused wave, if you want, right? Now, it's very good because it corresponds to the frequency at which you're measuring. And okay. Now, in 2007, the same team published an article with a very good title, which is Focusing Beyond the Diffraction Limit with Far-Field Time Reversal. So what do? They say they put a micro array of microphones very close to each other, so lambda over 30. They listen to it at lambda over 2. Okay, and what do they do to the microphones? They put copper wires next to them. Okay, so this is the experiment. And
So something to do some scattering, right?
yes, on your points, if you want, right? Very close to the source. And so first you send one signal. You send beeps from 1, 2, 3 from all of those points. You listen to it, and then you play it back, and you see, is it focused in either of those points? Okay. And there's lambda over 30 close. So normally you shouldn't be able to distinguish either of them. And so this is so position 3 and 4. This is the amplitude they get. This is their data. This is the sent back signal. Listen, now my 8 points are listeners. And so this is what I get on my at the required time on the 8 microphones. And you see that even though they are lambda over 30, you can easily distinguish one which was sent from the position number 3 and the position number 4. I mean, it's different peaks, much more than when you would expect from your resolution, right? And so they said that, as always, when you publish a set of titles, it got some press because it says a physical barrier has been breached and so on. And okay, and so
those scatterers that are next to the phones, they're also
they're not activated. They are just there,
just there to
in
scatter.
glue. Yeah, they are. Yeah. Okay, and so wow, I have 5 minutes left, so I'm not going to say everything about that, but what we wanted to know is, can you do the same thing for imaging, meaning that not with an active source or a microphone, but can you use the same type of ideas for passive systems where you have no source inside to find things? And is it really a random effect, meaning that, well, is randomness really important? Because I'm a very deterministic person, and so we try to create the same thing with a periodic deterministic structure and see if we can do it. Okay? And so, what should I do? 5 minutes?
Go ahead, 5 minutes over.
Okay. So this is your model. You have a Helmholtz equation, and this is your electropermittivity. You have your frequency is omega. And say you're sending a wave from, you're looking on a big disk, and so you're saying you're on a big sphere if you want, and you have a pattern phi, or if you prefer, you can write it in terms of traveling waves, but this is equivalent. And to say, normally it should be Maxwell system, but to stay simple, let's say we are looking at Helmholtz. Okay, and so what do we want to do? We want to image the effect of defects in this Helmholtz system, meaning that I have a nice medium, and I want to find if I can find this is passive imaging, right? I have a defect in my domain, just like before. This is my omega epsilon, which now I call D. I have a difference of permittivity or permeability somewhere, and I want to see if I can find something from the boundary. Okay, and I'm measuring my far field data, which is my phi to gradient u on the boundary, or my electric to magnetic field on the boundary. Okay. Let's see. So let's try with a very simple example. I have a disk, and in the middle of my disk, in the center, I have another disk. Okay, and and the radius of that small disk goes to 0. Well, so then, just like before, you recognize the formula. You have a polarization tensor. You have if you want, a magnetic moment tensor, or M, which is the same as the one we calculated in the same formula, except that you change your conductivity to epsilon. You have your response operator, the self-adjoint part. You look at what is the linear form of your problem. If you look at a given current and you test U against this current, you can symmetrize it, and so you look at this symmetric part, and this is what you get. Your background field U. So U is corresponding to phi or psi on the boundary, right? The effect of your inclusion is that your response operator, the difference between this and nothing, is something which is an integral on your subdomain. You have a constant here, which a matrix here, which in fact is, if you have two disks, is just a constant, which translates the difference of the contrast in permittivities. And you also have the magnetic effect, MB, which is just the contrast in permeabilities. Okay, same formula as before, except that you have 0 order term. That's very simple, and you can calculate everything because you're in 1 or in 2 or 3Ds. So this is spherical harmonics. This means that if you look at what this formula tells you, it tells you that you are projecting on your lower order modes. And so the first thing you see is up to the size of your inclusion is a projection on a cylindrical Bessel function, or spherical in 3D, which is located on your inclusion. Okay? And so this is what your response operator is. At first order, it's a projection on this eigenvector, which is so one first order eigenvector for the gradient part and 0 order for the 0 order part, which is the acoustic part if you want. And this is where things are projected. Okay, and it depends on k, where k is your frequency, so mu 0 epsilon 0 omega. All right. Bessel functions. So red is 2D and green is 3D, or vice versa. I can't remember, but this is 0 order 1, which has a focus size. This is the size of your central lobe. This is where a thing will be focused. This is your gradient part. It's the same type of behavior. Central lobes and smaller things after that. Okay. The size of your spot depends on this, on the size of this function, which is mu0 epsilon 0 omega. Okay? Very good. That seems that's really calculus. There is one information in all this, which is that, as you can see, the size of my central lobe does not depend at all on my inclusion. It depends on my background. Depends on mu0 epsilon 0, right? So whatever I measure, the size of my spot is the same. Okay, so introduce scatterers in your domain. Say, I'm going to modify my domain and put some scatterers. So let's say this is my object, and around it there are many scatterers to reproduce the experiment that was before, right? And so your you have so what do you want for your scatterers? Well, you have a periodic grid. It's deterministic. If you want to make them with certain symmetries to keep an isotropic medium, why not? And well, to have something interesting, you need the size of your periodic grid to go to 0 with the size of your inclusion. Otherwise, it's independent objects, of course, right? You have to take two limits together. But there is no ordering, meaning that it could be faster or smaller. It doesn't matter which way one converges with the other. They both go to 0. That's all. Okay. So what does your problem without the inclusion do? If you forget the inclusion, locally your problem converges to an homogenized problem, where you have changed your medium to an effective medium, A star, which is the average effect of your perturbations and the domain. So you have a corrector function. Your A is an integral, which is epsilon 0. I mean, it's epsilon 0 outside and something depending on your inclusion inside. Okay. And if you choose your things to be rods, then it will be isotropic because you keep the symmetries. And to have a measurement, of course, you want things which are not resonant locally. So you measure your difference, and what do you see? What is the result? The result is that your response operator has very much the same shape as before, same type of formula, right? It looks very much like the one I showed you in the, right? So you have M, a polarization tensor, gradients of U star, M star, U star, where M star and little m star are constant polarization tensors. They are not the same as the one in the constant case, but they have same type of properties. Okay, so what is the good thing? The good thing is that really you have replaced U0 by U star. So what you have done is that you have changed the size. If you put scatterers, you change the size of you change your effective medium, your homogeneous medium, your background medium to the effective medium. And so you have changed your size of focalization spot to a smaller size. And this is what's happened in the experiment, that his focalization spot has been changed to, because you have changed your medium basically, even though your inclusion is the same as before. So it's a local effect. And so if you did it, if you said, well, of course, I could have thought of that. So this is just small mathematics. If you say, I make my period go to 0, I homogenize my medium, and then I do a small volume fractional expansion, you get the right answer, meaning that you would get something like this with stars. You get the wrong constants, but that's not very important. But okay. If you do the opposite, this is what was a breach of physics. That he said, well, first I say I do a small, I look at my focal spot locally, so I do a small volume expansion. I have a point source, and then I make my period go to 0, meaning I forget my round medium. Well, in this case, the reference solution is epsilon 0, and so this is why this is what the mystery was, if you want. That in fact, it's not the way to calculate the background wasn't the background. You have changed your background. Okay, and of course, both formula go together, and I guess I'm already 5 minutes past, so I'll stop here. Thank you.
Very much. So, but I still don't understand. So what is